Good day everyone, and welcome to our first webinar in the new series covering drainage and flood modelling. And I'm pleased to introduce you to my colleague with me today, Ludmila Fadeva. Ludmila's been a practicing drainage engineer in the UK and over in the Middle East for 9 years now. And it's Ludi who will be running through the live demonstration after I've set up with a brief introduction to looking at flood risk assessments and modelling an ordinary watercourse. The plan is today to look at the kind of level 1 holistic level of flood risk assessments, and then in future webinars we'll get into more and more detail as we move through the series. So after this brief introduction, I'll look at some guidance and I'll introduce you to the Thatcham case study that Ludi will then show you live demonstrating with the XPSWMM software. And what we're looking at doing is modelling existing situations like the graphic shown there, where you have a natural, ordinary watercourse, and later on we'll add in drainage systems connecting into that watercourse and new developments, etc. With regard to the guidance, Series C624 came out in 2004, so it's 11 years young this year, and it covers the look at flood risk to new developments, but there's so much good guidance within it, we'd like to make reference to it, even though we're looking at an existing scenario, an existing situation with Thatcham. And one of the key things that came out of the guidance document is the fact that we have to do this right at the outset, at the planning stage. And the reason why I'm choosing Thatcham as a case study is because it was a rapidly expanding town in the late 20th century. And we're working all over the world. By the way, we've got 23 countries registered into the webinar here today. So there are areas of very rapid expansion, both still in the UK in certain areas, but also wider afield. Middle East, for example, I'm thinking of, with some really fast expansion programs going on. And unless we think about the surface water management at the outset, you're going to experience problems that we're going to share with you that we've experienced here in West Berkshire. We're also going to look at some flooding from the not so very obvious sources. The obvious sources would be the sea and for rivers, but there's also a high risk from some things that we may not have considered. Increasingly, things like higher groundwater levels affecting major infrastructure like the network rail, permanent way tracks, etc., and a range of other things as well. But we'll get into more detail with that during the series. And what we're looking at really is trying to make sure that we provide these sustainable developments for the long-term good of all. So looking at the guidance, I realize that you won't be able to see this screenshot, so I'm going to zoom in. We're going to look at the flood risk assessments, and there are 3 levels cited within the SERIA guidance. And within level 1, for example, there are 7 different sources of flooding that have been highlighted. There are actually more that we can show you later on in the series. But for the purpose of the exercise today, we're going to look at 4 of those 7. What we don't cover is flooding from the sea. We're not going to look at estuaries and tidal locked watercourses, and we're not going to model groundwater rising up, although I did mention the fact that this is becoming increasingly common, actually. But we can do things to replicate that, as Ludi will show you in the demonstration. So we're going to look at setting up a watercourse. So that will provide us with the source of potential fluvial flooding. We're going to look at extreme overland flooding. This is the pluvial. And then we're also going to make mention of artificial drainage systems. I'll reference them, but then we're going to model them in later series. And also looking at some major infrastructure failures. And again, I'll mention that during the course of this case study. So let's have a look at Thatcham, and to orientate people that are not familiar with the geography. We're broadcasting live now from Newbury, so in the middle of the screen there where the little teardrop is. Here's Newbury. We're about 45 minutes west of Heathrow Airport, which is here, west of London. And Thatcham is 5 kilometres to the east of Newbury, just to get yourself orientated. And we're located in West Berkshire. And if you can cast your minds back to the 20th of July, in the year 2007, we had a range of weather fronts that came across in the week leading up to the 20th of July. So it rained on and off every day. And what happened is, this is the town of Thatcham. So it's a rapidly expanding town. But basically in 1951, there were 5,000 people located here. Now there are over 25,000 people located here. So it's expanded 5 times over about 60 years. And the east side of the town is the area that has been developed more recently. And if you can just remember this little triangle down in the bottom right-hand corner where the mouse is now, that's a detention basin that's just around about 0.5 meter towards 1 meter deep, a depression in the ground. I'll show you a photograph of that, and Ludi will show you an analysis where the flooding has found itself into that location at a slightly later date. So on the 20th of July 2007, it started raining, and it didn't seem to stop. We had a 6-hour rainfall event, and it generated about 3 times the normal daily rainfall on that particular day. But what had happened previously is that all the ground had become completely saturated because there's other weather fronts. So it was the kind of straw that broke the camel's back. And in terms of the topography, again, Ludi will show you with the software the topography a little bit more graphically. But if you can just think of the northern part here where the mouse is, this is the hillier part, the higher land. It's not mountainous, but it's higher. So when rainfall lands on this rural area, you can see it's predominantly farmland, lots of different fields and things here, and some woodland. The rainfall will create runoff and then try to flow south. And as we go down through south, we've got some natural barriers here. This is the A4 road. It's a major highway. As we come down to the south of the town, there's another line that you can see here. This is the railway line. And it's not a railway in a cutting. This is a railway upon the top of an embankment. So it's a man-made dam. So the water is flowing down across the topography and it will get caught by the embankment. Over to the east again, from this area that was more latterly developed, there's a pipe that runs under the railway embankment, and it's a siphonic pipe. Because of the levels, it kind of goes down and then has to come back out again. I'll show you a picture of that pipe. It's the main outfall from this part of the town, entering into the River Kennet, which you can see here, a little elbow of the river. And we have a watercourse here, a canal. So Ludi set up a model. We're not trying to totally replicate what happened on the 20th of July, because that's already been analyzed by some really good consultants and the local authority. But we're showing you the elements of how you can get a good idea about flooding and a level 1 study from the outset in a really quick and easy way. Now, the really interesting thing to me about this was that I've crossed out fluvial here. I mentioned the 4 elements that we're going to focus on today. Yeah, Ludmilla's going to set up the watercourse for us, but also to note that there was a little bit of flooding, but not major. The return period actually was a 251-year return period, 6-hour event. This is flooding shown here in the highway. This isn't a river, and this is not a source of flooding from the river. This is a source of flooding from the pluvial, the extreme runoff coming from the north of the town and washing through the town. And look at the color of the water. You can see that it's mobilized and picked up soils along the way. In terms of the artificial drainage system and the outfall pipe that I mentioned, the siphonic pipe, this is it. And this is it 2 days after the event on Sunday, the 22nd of July. So the previous photograph was at around about 2:30 in the afternoon, and the cars were being washed down the road of the parents trying to pick up children from school. Now, on this particular outfall pipe, you can see a safety grid. So the health and safety police have been out there. They don't want people climbing up the pipe, but that's a bad design. So more of that in future webinars, but that's how not to fit a safety grid onto a major outfall pipe, because you can see the debris trapped in there, and that would not have alleviated any flooding. We would have had flooding, don't get me wrong, it would have flooded no matter what. This was a really major 251-year event after a succession of rainfalls that happened in the lead up to the one day. But what would have happened is that the inundation, the time the water was sitting and flooding people's properties, that inundation level would have dropped more quickly had the water been allowed to have discharged at a higher rate. Again, Ludi will show you some of this the inundation mapping live with the software. Remember the little triangle that I mentioned in the bottom right-hand corner? That's the triangle here. This is a detention basin around about a half a meter to a meter in depth on average, normally a dry basin. And this shot was taken 2 days after the major flood, which is in the bottom left-hand corner of the screen, where the cars are getting washed down the road because they're trying to pick the children up from school. There was a safety rope across the road, and people were trying to evacuate. Perish the thought of them being washed away. Thankfully, we didn't have any fatalities. But we feel quite emotive about this because 2 of our colleagues who are still here today were flooded in that event. So we've got personal experience of that ourselves within the office. This shot, I know it looks a little bit grey, but you could maybe, when we are recording this, by the way, for you to replay at your leisure, but you could maybe pause on this and zoom in later on. But what this is showing you are the little red dots, which are probably hard to see, but there's a lot of little red dots. So you can see like a V shape, come U shape going across the map here. And there are a lot more dense dots in this area here. These are all the properties that we're putting in flooding claims. There were 1,100 properties flooded in this one event in July 2007. So I think that's long enough of an introduction, and I'd now like to hand you over to Ludmila to show us how you can create the models and look at the flood risk assessments level 1. So over to you, Ludi.
Thank you, Peter. As Peter mentioned, we are going to look at TOCHM today. So first, I would like to start with the topography of TOCHM. If I just take a section profile, make a line from north to south. Okay, so if we look at the profile, you can see that it goes from north down to south and it slopes down. So basically, all the water which will appear on the top of the hill will naturally find its way down towards a river or a canal which is located at the bottom. So we know the topography, but first of all, when we look at the Syria guideline and a flood risk assessment level 1, so the first item which is mentioned is fluvial flooding. So what I'm going to show you first is how to set up a watercourse in XPSWMM software. So what steps you need to undertake to do it. I will zoom in on a particular part, and in here you can see this is a small tributary which is joining the channel in here. So if I would like to add it to my model, all I would need to do is select a river tool and just draw a few lines, few nodes, few links. So I will just do 3 links, 3 nodes. It will ask you to give it a name, so I will just type in name. Doesn't matter at this point. So what we will have is a small watercourse. Each watercourse needs to be described with a cross-section. So at this point of time, I won't connect it to the channel which we already have set up because it may mess our results. But we did run this model for 48 hours before, so we don't want to keep you for 48 hours to see the results. So, but potentially you can connect it to any of the nodes of your watercourse and make it as a tributary flow. So to describe the cross sections of this small watercourse, all I need to do, if I have a good DTM, obviously, I can ask the software to read the sections from the DTM. I go and select the Calculate Conduit Cross-Section tool. I would like to do it only for selected links, so I don't want to replace any of the existing sections I have. I will use my DTM to read the sections from. I will read them from upstream node and offset it 50%. That will mean it will take a section somewhere in the middle from upstream and downstream node. And I would like to take sections 40 meters right, 40 meters left. I will say OK. I get back a notification saying that 3 links have been assigned a shape. So if I say OK now, you can see these yellow lines which came up. So these are the locations where the section was taken. So now, if I just double click on any of the links, you can see that there is a shape assigned to it. If I click edit, you can actually see the shape. So we can see that this shape, maybe it's not exactly the shape which is of the watercourse. So if I don't like it, I can just remove it and replace it. Or what I can do as well, I can delete it, delete this cross-sectional layout from that particular link and then redefine it for that particular link. And I can define it just manually drawing a line. Right? So if I say OK and then I double click again, go edit, so now it looks better. What I need to do at this point of time, I just need to identify my left overbank and my right overbank. So when I define my overbanks, you can either do it using these small tools at the top of the window, or you can just write a chain each, what is your left and right overbank. You obviously need to define a Manning coefficient for your watercourse. We have two ways of defining it. It can be either a simplified Manning coefficient, left, center, and right, or you can use a depth varying one. So if you have a good data and you've actually been on site and done some assessment, if there are any bushes, trees, or grass growing on the bank, so and you measured at which depth each of them appears, you can say, okay, for that depth, my roughness will be this much, for different depth, it will be different. So it's up to you and how much data you have, if you would like to define a varying roughness, or you would like to stick with just free values. Okay, at this point, what I will do, obviously for each watercourse, we need to add inflow, right? So we have different ways to add inflow, but I will show you inflow parameters on the existing channel, which I already set up. At this point, I will just delete this new build river, so it doesn't appear in the results with some zero values because the model was not run for it.
Ludi, can I just interrupt a second?
Yes.
We've got some questions that have come in. You just sort of defined a tributary as a 1D kind of link and node. What about if someone's already modeled a river and they've done that in some other kind of a software, third-party software? Can you import something that's already been done elsewhere?
Okay, thank you, Peter. At the moment, we have few importing options. If you have a 1D model in HECRAS, you can import it. It will import bridges, culverts, and all the data of your watercourse. If you have any sections, pipe networks set up in microdrainage, you can bring them in as well. Or I know some people, especially outside of UK, are using IPA-SWIM a lot. So we have an IPA-SWIM reader where you can bring in IPA-SWIM 4 or IPA-SWIM 5 models inside the network. I hope it helps.
Yeah, thank you.
So, talking about inflows. So what I've done for this watercourse I've set up, I set up an initial depth because I know historically from the measurement which was done, the initial depth of this channel never goes below 95 centimeters, and I've done some constant inflow, which is 3.1 cubic meters per second. As well, from historical data, we know that this is the usual state of the watercourse, and there is always an inflow of this much. I didn't add any hydrograph at this point because I have two scenarios in my model. So one scenario has no input hydrograph, and the second scenario will have an input hydrograph. But what I have done for a top node of my model, a river model, in a runoff mode, and runoff mode is the mode which describes your catchment. I have set up a catchment of 50 hectares, 100% impervious, and I assigned a rainfall 251 years return period, 6 hours duration, rainfall event for that catchment. So after I ran the model, I can see the results for that runoff node, and I can see actually how the water is contributing towards that river node. What we can see, obviously, there is some initial time for water to travel over the catchment, because we do define catchment width and slope. So the software will calculate how much time the water takes to reach towards the node. So we have some delay of 1 hour before any water reaches the node. But then we can see how our runoff goes up, and it continues to go up, and actually it doesn't go back down. So we did run the model for 36 hours. So you can see one day, don't worry that here it says January, right? Because you can actually set day and time when you're running the model if you would like in your report to have a specific date. But if not, in this version, it's 2013 version of software, so it starts January 2014. So Wednesday 1, Thursday 2, it's 24 hours, and then another 12 hours. So we did run it for 36 hours, and you can see that our inflow doesn't go back down. So it indicates to us that actually the catchment hasn't drained down yet. So for us to know when the catchment will stop draining down, we would need to extend the time of simulation. But for demonstration purposes, it's fine. So we are not that much interested to know when the catchment will completely drain down. We just want to show you different ways of how you can input inflows to your 1D watercourse. So you can set up, if you know your catchments which are contributing towards your river, you can set up as many of those catchments as you have nodes, and each node can have up to 5 sub-catchments connected. So they may have different impervious percentage, width, slopes, different rainfalls assigned. As well, one thing to mention in here, I have 0 infiltration selected, so it's none. And the reason is, as Peter mentioned before, as the ground was very saturated, so there was no infiltration possible. But if you want, you can set up an infiltration, and then you will have some water loss through infiltration. Or you can set up evaporation alongside if you are somewhere in Middle East or any other location. Like I know we have a couple of people from Greece who are here today with us, and if you have a lot of sunshine, you will have evaporation, so you can set up your evaporation values as well. If I go back to hydraulics node, and if I choose scenario 1, in the scenario 1, what I did, I have assigned as well a user inflow hydrograph to my model. So there will be some extra flows. So everything will be the same, initial depth, constant inflow, catchment which is contributing is staying exactly the same. But what is coming extra is user inflow. So it's time against flow, a typical hydrograph. But sometimes I know we have gauge data for watercourses, and if you have any gauge data, it can be either level gauge or it can be flow gauge. You can assign a gauged inflow. You will just select a file where it's kept. There is a certain way how to set up a gauged inflow, which we cover in our training, which is happening, I think, next time, end of September. So if you would like to join us, please feel free, visit the website. Yeah, but you can, there is a possibility to assign a gauged inflow to your watercourse. As well, there is such item which is called gauge data. So this is for calibration purposes. If you have any historical records and you would like to replicate any event, and then you would like to compare how your model is performing against the actual data, you can attach a database file for either gauged flow or gauged level. So the difference is, in a node you can assign the flow, and in a link you can assign a level. And then you will have in your results, you will have different lines which will allow you to compare your actual results to your historical data. So if I now select downstream objects for that watercourse and go dynamic long section, I can just play it and we can see how it works. So nothing critical is happening. So the water goes up, the water goes down. So the long section is one of the items which is as well available for you to review your results. What I'm interested in now, I would like to check for node 10. So I just clicked on labels to bring the node names. And node 10 is a node which is important, and I would like to measure some results in node 10. I can go to table list. So tables are set up manually. You you preset your tables, and then you can select different type of results. There are many type of results available. So, but I chose only few: duration of flooding, maximum water elevation, and maximum water depth. So if I just focus on node 10 and see duration of flooding for node 10 base scenario, it's about 24 hours duration of flooding and maximum water depth of 1.06. If I change this scenario for scenario 1 and go back into table list, you can see the duration of flooding for node 10 has increased. Remember, we had a hydrograph assigned to scenario 1. So because of extra flows, we have more time the flooding happened, and we have more depth in the channel itself. So it went up about 300 millimeters. So instead of being 106, it's now 1.37. It's 31 centimeter increase. As well, I have a table set up for links. So in here, you can measure the volume, velocity, maximum flow, again, maximum depth parameter for the link. Again, you can bring more results in if you would like to see more, but how to set up a table, it's a separate part, again, of our training course, so feel free to join us for the training.
And just a quick question from Sophie. I'm trying to answer the questions as we're going through, but there's a kind of timely one. In terms of the different return periods and the different storm durations, you can run like multiple return periods, multiple storm durations on the different models.
Yeah, you can set up scenarios. So basically how it works, when you set up your base scenario, you may say if you would like to determine your flood zones, flood zone 1, flood zone 2, flood zone 3, 3A, 3B, so you will have different return periods for each flood zone. You can set up your base scenario as, say, 1 in 30, and then if you click New, you will have a copy of that scenario. And then when you go actually, I would delete it now, right, so it doesn't mess everything, but actually when you go in any scenario, and if you go inside any node, right, so in here, you can define a rainfall for that particular scenario. So you can run one scenario with one rainfall, another scenario with another rainfall. Similarly, if you are in hydraulics mode, you can define these different user inflows for different scenarios. You can different gauged inflows for different scenarios. So it's all up to you and how much data you have and how many scenarios you would like to run. So it's all possible. It's not like in micro drainage where you run all in the same scenario, but you just need to set up a separate scenario for each rainfall event or each condition you would like to test it for. So this is all very nice and good. This is 1D setup. So we have a 1D watercourse. We can measure the levels. We can see the duration of flooding, velocities, volumes of water, but we don't know where this water goes, right? So as soon as it leaves the river, we have no idea if it floods on one side or on the other side of the river. I will just untick the labels so they don't mess. So what we need to do now, we need to set up a 2D part of our model. And what I did for that particular model, I have two different grid extents active in this model. So one grid extent is called town, and it's up to you how you call your grid extents. You can have multiple, and it's 5 by 5 grid step size, so it's very dense. And if I just zoom in, you can actually see that, maybe I need to zoom out of it. You can actually see that it covers in much detail our DTM. And a second grid I set it up is called hills. So I set up a separate grid for a north part of the development to actually to do one thing for that, right? So and that grid is different sizes, 50 by 50, because actually I'm not interested in any flooding analysis for the hilly part. I'm interested in flood analysis for town. But what I want to do, because that event on Friday, 20th of July 2007 was mainly caused not by fluvial flooding, but by pluvial or overland flooding. So what I did, I used a function called rainfall flow areas, and I applied it on top of a big grid, 50 by 50. And I assign it, so it's like a sky, it works like a sky which will rain on your grid cells. It will make each grid cell underneath wet with either hydrograph or a rainfall file you attach. So I attach the same file, 251 years, return period, 360 minutes. And it will rain for 6 hours on top of a big grid. And what will happen next? I added one more line, very important line, which is called 2D interfaces. So it's maybe not very visible on your screen, but if I untick the background image, you can see this line in here. Right? If I double click on this line, this is a tool of TwoFlow, right? So our 2D engine for the XPSWMM software is TwoFlow. So when we connect two different grid cells in TwoFlow, we need to identify which grid is connected to which grid. So it doesn't matter which way you connect them, because it will just say that there will be a water exchange in between these two different grid extents. But what is important is to identify the minimum distance between 2D connection. And as TwoFlow manual advises, the minimum distance should be at least twice more than the maximum grid cell size. So my maximum grid cell size is 50, so that's why I used 100. So this is a useful tool to have multiple grids when you have a bigger area and you don't want to have dense analysis for the whole site, but you're just interested in some particular part. So you can use multiple grids to determine it. So yeah, we have two grids and a connection.
Sorry, Lily, can I interrupt this? I just want to thank everyone for the questions, by the way. I'm typing away here trying to answer the majority as I'm going through, and I'm running to stand still. But the one that's come in here now is the limitations potentially on what about the grid cell sizes? I mean, you've got the 50 by 50 and a
5 by 5.
5 by 5. Is that, you know, what are the options available basically on the grid cell sizes?
So basically, there is no restriction. You can go as small as you like. You can type 0.1 and the software, so it's 0.1, yeah, and the software will regenerate the grid to be 0.1. But what you need to be careful of is your DTM data, right? So if your DTM data, say if you have a measurement of a level on your DTM data every 2 meters, there is no point going with your grid cell size less than 2 meters, because your results won't be more precise. It will just eat some simulation time out of your time, but it won't give you better results. So you would usually go same size as your DTM data or bigger if you are happier to have slightly less precise analysis. The sizes which environmental agency defines in their manual, I think up to 5 to 5 is a good size. A lot of people do 2 by 2 analysis, but yeah, you have no limitations on the grid cells.
That's another good point, because in terms of the outputs, this is something else we'll do in later webinars, by the way, folks, but there is a surface water mapping, surface water flooding document that the EA and DEFRA produced, and there's a table in there highlighting the outputs that they actually specifically want and sizes of grid cells, etc. No matter what we've run, we can output in those sizes. So we'll show that in a later webinar. Sorry to disturb.
Yeah, and you can have as many grid extents as you like as well. So there is no limitation. It's not like 2 or 3. You can have 5, 10 if you want. Obviously, you will need to have a 2D interface layer for each interface which is talking to each other. What I will do, I will just stop on one more item, that for our river, we need to make sure that our river crest is connected to 2D, right? So the water which leaves the 1D model will flow onto 2D. So now if I play the model, if I just select the base scenario and click water depth and just play it, so we can see how it moves. If I just play it, you can see that it is raining on the hilly side, and you can see how the water goes down as a function of a natural topography. And if I just pause it at this time, see, it's 5 hours from the beginning. If I just zoom into the river at this point, so it's 5 hours, 12 minutes. What you can see, we have some flooding happening out of a riverbank, but actually, it's not major. There is nothing major happening along the river. So we have all these extra inflows and we have big catchment connected, but there is nothing much out of our fluvial analysis which may cause such a major flooding which happened in a Tachum town. So going back to Syria guideline, right? So fluvial one is number 1 in the flood risk assessment level 1. So it's number 1 on the list. But at this particular point, that's not the major flooding source. So if I just untick the water depth and go to maximum water depth map, right? What you can see, remember the insurance claim map which Peter showed you. Remember this U-shape, V-shape, or V-shape, U-shape, and V-shape, right? And remember that small detention pond which he talked about, and the pond was wet even 2 days after the event. So this is the location, this is the detention area with some benches located around here. And if we scroll with the mouse across it, you can see that the water depth is 0.5, 0.58, 0.6. So again, depends on how good your topography is, but it represents what actually happened. And all these red dots, a lot of red dots in this eastern side of the development who claimed the money from insurance companies. If we look at this map, it's all flooded. So what we did today obviously didn't include any artificial man-made drainage systems, right? So we don't know how much water would actually go into a drainage system. But what we as well excluded today from the analysis is that it actually rained on top of a town as well. So we didn't make it rain on top of Tachum as such. We only made it rain in a hilly area. And we did it for this purpose. So you can see how actually we can route the water and how the water can be routed through different grid cell sizes. And that we didn't make it rain on Tachum itself, but we still can see how much an impact a rain of this return period and duration can bring to the town. Now, if I just go, so if I zoom in at certain location in here, remember where I tried to build an tributary flow towards our channel, and if I now change a scenario to scenario 1, you can see how the flood map changes, the maximum water depth. Let me do it again. So this is base scenario, and remember in base scenario we have no extra hydrograph connected to the watercourse. And in scenario 1 we have an extra hydrograph contributing. So you can actually see that the water level in the watercourse goes up and it kind of floods the tributary, which is not the case in real life, because in real life this won't act as a storage. This will be as a flow which is contributing towards our main channel. So probably when we do the real life scenario, we would need to set up this tributary as a 1D function. So we have it excluded from a 2D, and then all this water, which is now actually accumulated in a section here, it will redistribute in the areas around. Peter, I can see one question coming on what are the benefits of integrated 1D, 2D modeling?
Yeah. I'm getting through the questions as well here, guys. So I'm up to about 12:34. So if we run out of time, don't worry. We'll send out answers to those that we've already gone through, plus answer the ones that are left behind. Yeah, the 1D, 2D, the questions come in. Why don't you just set everything up as a 1D, like the watercourse and the drainage network, and then run that? that is the best accuracy in terms of the hydraulic performance of those networks. But the problem, or the limitation, I suppose, is when the flooding comes out, we know accurately what the volume coming out of the network is and where it's coming from, but we don't know how that then interacts with the surface, so the depth, the direction, and the velocity of the overland flow, which is where the 2D comes into play. So the other question that came in was, why don't we just do the 2D? Well, that then becomes an issue when you have the 1D channels, etc. If you had a large grid cell size going across a relatively small watercourse or where the drainage network is, you're potentially going to have an inaccurate result for that channel just with the 2D. So the combination of 1D and 2D basically gives you the best of both worlds. And as Lud has just zoomed in there, you can see the sort of boundary condition between where the water would overtop the bank and then go onto the surface, and where it would come from the surface and then overflow back into the 1D watercourse. It's the best of both worlds, and the most accurate replication of what's actually there.
And this line in here, which is the railway, which is in embankment, so you can see that the water can't travel over the embankment of the railway, so it just starts ponding at the edge of it. And
that's so typical. If you have a railway or a road, like the motorway networks, and typically we'd have a culvert, if you had that, if that was a low point in a ditch or a swale or something coming down to that point, that's the point at which we'd normally have a larger size culvert going underneath it. And typically this is where we end up with a lot of problems, with siltation, trash, lack of maintenance, etc., everywhere.
So what we will do in our next webinar, we will use exactly the same model, but we will add the drainage systems and we will add the culverts which are crossing the railway, and we will run it and see how actually it helps to alleviate the flooding. And we will run a scenario where the culvert will be firstly blocked like it was in real life, and the other scenario where it will be free flowing. So, and we can then compare how inundation time can be reduced by maintaining the major infrastructure.
Yeah, exactly.
That's it from my side today.
Perfect.
Back to Peter.
Thanks, Ludi. I've answered quite a few questions there, folks, but there are some more kind of coming in. From George, which is the better to use, the XPSWMM or the XPStorm when you're looking at the sort of flash flooding? The difference between the two, George, there is that XPStorm is purely stormwater, whereas the XPSWMM includes the foul water networks as well, sanitary, combined sewers, those kind of things. So if you're looking at the combination of everything, you'd be working with XPSWMM. If you're purely looking at the stormwater, then you would be working with XPStorm. There's a question about the mesh. Do we use a flexible mesh? Yeah, so no, we're using it because it's two flow. We are using variable grids, but not variable mesh. So the engine for the 2D overland flood analysis is two flow, which the EA particularly like over here, for example. So that's why we use the two flow system and the grid system rather than the flexible mesh.
There is a question what type of DTM data is required, and basically you can use any DTM data you have. So the more precise it is, the better results you get. So you can use either just simple topography survey, which you do manually. Then you just put it in the XYZ format and import it into software. You can use LiDAR data, ASCII raster files. So there is a long number of different DTM input sources available.
And there was a question about the fact that we were just applying rain on grid and some inflow from catchments, which were mainly looking like they were rural. But just to reassure you that as we go through the series, we will be looking at more detailed modeling as we go through. This is kind of looking at level one, the kind of holistic. What kind of understanding can we get fairly quickly? And I'm thinking of folks that are working maybe on new developments and having to look at the existing catchment, because we need to be mindful of the impact of a development upon an existing catchment, but also the impact of the existing catchment upon the new development. So it's that kind of work that we're looking at in this initial survey, in this initial webinar. But in future webinars, yeah, we will definitely be modeling the existing drainage networks, so those critical infrastructures like the culverts crossing underneath embankments, showing you how you can replicate the siltation, and you can have different scenarios with different depths of sediment. So, what if the whole culvert was blocked? What if it was half blocked, et cetera, et cetera. And we can add in runoff from urbanized areas, from roads, from properties. We can add in flows from sanitary systems. We can mix everything together, create combined systems, etc. So
yeah, stopping on combined system, we have a question: how would the software interact with the local sewer networks? Are there any ways to account for the building storage and add CSOs? Yes. So next webinar we will show you how to add drainage systems to that particular model, and we will link the drainage systems to 2D, and we will allow water to spill out of a drainage system and and join back in drainage system, maybe somewhere down the stream, where the capacity is. And basically all the water which will be within the drainage system, it will be stored in there, and you can account for that storage as well. We have one example on CSOs. If, by the way, you want to know more, obviously we can't show everything live. Just drop us an email, and we will be more than happy to demonstrate it for you online or in person.
Yeah, and thanks for the great feedback as well, Michael. Just to pick up on your question about replicating the saturated ground, yes, we can. Again, in a future webinar, what we'll do is we'll bring in land usages through GIS. And then that land use, it may be different types of field. And what we can do is we can zone them. So by reading in the attributes of the GIS, that becomes really powerful, because then we can say, okay, in this rural landscape, this is all kind of crops and fields, etc. And we can then pre-saturate the ground condition for those particular zones. And we can highlight buildings, and we can highlight road areas, etc., and have different runoff characteristics, as well as say pre-wet the ground to really drill into the detail of what it was really like on that 20th of July before the rainfall arrived, and then apply the rainfall event, which, by the way, is an actual measured event. The storm cell happened to go right across an amateur meteorologist's weather gauge, rain gauge. And so we've actually got that recorded event, and that's what we can apply onto the model.
We have a question on which mathematical equations the software is based. So in terms of 1D, we have different routing methods in there, starting from XPSWMM runoff method, the 5 rational method, SCS, 5 UK methods. And in terms of 2D, it's a full Saint Vernant equation, shallow water equation. Yeah, so it's a two-flow full shallow water equation.
Yeah. Okay. I think what we'll just take a look. There's a lot of questions, and I really appreciate the interaction. It's obviously stimulated a lot of debate, and it's much appreciated. It makes our lives a lot more interesting as well. So I think we've hit a spot with a lot of what we've shown already. Feel free to share information with us. What I'll do is just go through the...
Just one last question. Sorry, Peter. Okay. There was a question if we can replicate a bridge.
Oh, right.
Yeah, okay, so yes, for sure, we can model bridge in 1D, and we can model bridge in 2D. And on our website, we have a separate webinar which covers... it was presented by our US team, and it covers when to model bridge in 1D and when to model bridge in 2D. So if you're interested, just have a look, or just drop us an email, and we will direct you where this information is available.
And we can show you. If there's anything specific, there are quite a few guys and ladies that are sending in questions relative to their specific projects. I mean, do feel free to send us some information that you do have, and we can show you how easy it is to pull together some form of a model for you within XPStorm, XPSWMM. I mean, that would be a pleasure to do. We can do, we do a lot of webinars away from the public ones. This is why we run them every kind of 4 weeks, because in between times we're doing a lot of specific things apart from the training and attending and presenting at conferences and what have you. We're doing a lot of one-on-one kind of webinars looking at specific projects. there's some. I'm very excited about the potential to show you some case studies that we've been working on right now, and there will be some flooding coming from some very, very unexpected sources affected some very famous landmark infrastructure, and I'll leave it at that. And we've got some approvals to go through, but that will be great. So hopefully we've whetted your appetite, and you can see in terms of the flood risk assessment type work that you may have, and just setting the scene at this kind of higher level, level one, the kind of capabilities and the speed and accuracy of what we can do with minimal information in a way. We can set up some watercourses to replicate that fluvial condition. We can have flow either coming off of the grid into the river, or those user-defined inflows, as Looney showed you. We can put in the base flows and set water levels within the watercourses before the rainfall hits. And we can have a range of sub-catchments also enter into those watercourses at variable places. So not a problem. In terms of the extreme runoff, those real extremes like the July 2007 situation, the pluvial events, we can set those up with rain on grid. We can have the existing drainage systems incorporated into the models that we'll get into in the next webinars, and as well as those new developments. And those new developments may be designed typically in micro drainage. Bring those models in, and then look at the impact of the new development upon the existing situation. How does it affect the water levels, flooding, or not, as the case may be? Fully understanding the amount of technical output that you need to provide people nowadays to reassure that you're not adversely affecting a situation and making an existing bad situation worse. So it's all about the outputs as well, and convincing people. And that, I think, if we go on to the final slide there, Ludi, just to let you know, we're running, I mentioned the training and conferences and what have you. 6th to the 10th of July is the next training series happening here with regard to micro drainage. Our next webinar with XPSWM will be on 22nd of July, where we're looking at that impact of a new development upon an existing scenario. I put a couple of question marks in there. We are running XPSWM training here in September, but also I'll be in the Middle East in August. Well, I say August, I'm waiting on confirmation, so you know how that is, guys. But I will be over there in August. So if there's anyone looking for training in the Middle East, let us know, because I can schedule things in with enough notice. And then in September, we're penciling in for around about the first week in September to Ireland. We had a lot of inquiries in from there as well. So I hope that will help and save you a little bit of traveling yourselves. And it'd be great to meet you all. Meanwhile, thanks all for your interaction and for listening. And from
Thank you very much.
Yeah, and from me, have a great Ramadan, and we'll speak to you again on the 22nd of July.